Lesson 8.1 is Spearman's rank correlation coefficient. In chapters 3 and 6, we talked about Pearson's product moment correlation coefficient, which is for strictly linear data. Spearman's rank correlation coefficient can be used for rank data or nonlinear data. So I would take a minute to pause the video and write down these notes. So Spearman's rank correlation coefficient, we denote with an R sub s, so R is still our correlation coefficient variable, and it's a product moment correlation coefficient for ranked data. So if your data isn't ranked, as in like you gave somebody a list of things and asked them to rank it from their favorite to their least favorite or something, then you take the x coordinates and you rank them from highest to lowest or lowest to highest, and then same thing with the y coordinates, whatever you picked for whichever direction you pick for the x-coordinates, you do the same thing for the y-coordinates. Now that rank value is your new x and y coordinate that you then find the product moment correlation coefficient for. Monotonic means that your data is only increasing or only decreasing. So when you're looking at ranked data, you're looking at how it's increasing or decreasing. So if your Spearman's rank correlation coefficient is equal to a positive one, that means your data is strictly increasing. If it's equal to a negative one, that means your data is strictly decreasing. If it's closer to 0, that means it's neither increasing nor decreasing. There's not really a relationship between the ranks of one variable versus the ranks of the other variable. So the way we're going to find Spearman's rank correlation coefficient is first, like it said, we have to rank the data. I'm going to go from lowest to highest for both the x and y coordinates. So the first thing I'm going to do is I'm going to look at the x coordinates for this example A here, time spent training in hours, and I'm going to rank them from the smallest amount of time to the largest amount of time. So here I've ranked the x coordinates from smallest to biggest. So C was our smallest x value, our smallest amount of time, so I ranked that as 1. And then A and D are tied. So the way that you do something that is tied is you take the average of the ranks. So in this case, it would be ranks 2 and 3. So you'd rank 2 plus 3 divided by 2, so they'd both be ranked at 2.5. If there's 3 things that's tied, you take the average of the 3 ranks that they would equal, and then that would be the rank for all of them. And then E is number 4, B is number 5, and F is the biggest one, so I rank that as number 6. So go ahead and pause the video and rank the y coordinates, time to run 2 kilometers in minutes. Again, rank it from smallest to biggest because that's what we did for the x coordinates. So in this case, our smallest amount of time to run a 2K was F, so that's number 1, B is number 2, D and E are tied for 3rd and 4th place, so they're 3.5. A is 5, and C is 6. So now the way that we find the Spearman's rank correlation coefficient is we ignore the actual times that they give us, the data they give us for x and y, and our new x and y coordinates are the ranks. So those red numbers here are our new x values, and our blue numbers here are our new y values. And then we find our normal Pearson's product moment correlation coefficient. So go ahead and pause the video and find your correlation coefficient just as if this was linear data using the new ranks as your x and y coordinates. So doing it the same way, again, list 1 our x coordinates, so that's the red ranked values. List 2 are our y coordinates, so that's our blue ranked values. And then you go through, do your linear regression to get your r value. So now we have this r value of negative 0.956. But this is the Spearman's rank correlation coefficient because we use the ranked values instead of the actual x and y values. So this is how well the rankings of them fit. So since it's pretty close to a -1, that means that it's almost strictly decreasing. So the more time that was spent training means there's a shorter amount of time to run a 2K, which kind of makes sense. So now try the same thing for this next one for B. So again, rank them, choose highest to lowest or lowest to highest. Either way, just make sure you're consistent with your x and y coordinates. So rank your x's, rank your y's, and then find the Spearman's rank correlation coefficient. So again, I ranked it from lowest to highest. It doesn't matter. You would end up with the same answer if you ranked from highest to lowest. I always just start with the smallest. So the number of pets is already ranked from smallest to biggest. That's why I went that way. And then the time spent carrying, it's almost perfect except for there's 2 8 hours here. And since I went smallest to biggest, it would be ranks 3 and 4, so it's 3.5. And so you end up with a Spearman's rank correlation coefficient of 0.975. So because this is very close to a positive one, it's almost perfectly strictly increasing. The only thing is that these two here are the same, so that's the only thing that makes it not be a positive one. So here's an example of when we would use Spearman's rank correlation coefficient. So a student was asked to rank 9 different makes of burgers in terms of which she liked best to least. She put 1 for the one she liked the best and 9 for the one she liked the least, and those are being compared to the cost of the hamburger for each of those hamburgers. So before we go ahead and calculate the correlation coefficient, go ahead and pause the video and explain why you can't use Pearson's correlation coefficient in this example, why we have to use Spearman's rank. So for this one, the reason that we have to use Spearman's rank correlation coefficient and we can't use Pearson's product moment correlation coefficient is because the independent variable is already a rank. It's not raw data. Raw quantitative data, it's already a rank, so it's not necessarily going to be modeled by a linear regression. So now that we've decided why we have to use Spearman's rank correlation coefficient, go ahead and pause the video and actually calculate Spearman's rank correlation coefficient and comment on your answer. So again, independent variable is already ranked, so we just need to rank the dependent variable, the cost, and then find your Spearman's rank correlation coefficient. On this one, it does matter whether you rank the cost from smallest cost to biggest cost or the other way around. If you rank from smallest cost to biggest cost, you end up with a negative correlation coefficient. If you rank from biggest to smallest, you end up with positive. Either way, it ends up being 0.8, so a moderately strong correlation. It's just whether or not your rank is increasing or decreasing. Either way, with a few exceptions here and there, as the taste rank increases, which means she found it less appealing, the price will decrease. So basically, the cheaper the hamburger, the less tasty it is. Here are last few minute details about Spearman's rank correlation coefficient, specifically in connection to Pearson's product moment correlation coefficient. Remember, we use this sub S to represent Spearman's rank correlation coefficient. Without it, it would be Pearson's. It's only valid for the data that's given. So unlike Pearson's product moment correlation coefficient, you can usually create a linear regression and do some interpolation or predict other data. It only works for the data that you're actually given. You can't use it to make predictions on unknown data. Also, if data points are similar, like if the values are close to each other, small changes could affect the value. So there's a lot more cause and effect that happens on your Spearman's rank correlation coefficient. Some advantages over Pearson's product moment correlation coefficient: it can be used for nonlinear data. So if you have something, let's say that's like exponential, you can rank the x and y coordinates and model it with this kind of linear ranking system and then find the correlation between them. It can also be used on data like the previous example that we have that's already ranked, where the original data can't be quantified or is unknown. So it's useful if you're like testing things like the previous example, ranking hamburgers or something. It's also not greatly affected by outliers because you're just giving it a rank and you're not using the raw data. It doesn't matter if that last data point is, very close to the original data or if it's way far off. It's not, you're just ranking it, so it's not going to affect the overall value of your Spearman's rank correlation coefficient.